Okay, so we've talked about a Lewis dot diagram. A Lewis dot diagram is very important. We know that we've seen it in many past year papers, so you must be able to draw a Lewis dot diagram. Since it's so important for tomorrow, we're going to just focus on how we do this, a Lewis dot diagram. So your first step in drawing a Lewis dot diagram, so for instance, if they tell us, draw a Lewis dot diagram for, let's say, sulfur. Your first step in this is going to your periodic table and you're going to find out how many electrons is in sulfur. That's the first thing we do. So if we open up our periodic table, okay, I've got it here. Just going to zoom out. So if we look for sulfur, you obviously have to know your symbol for sulfur. We know it's a capital S, and we can see above sulfur we've got 16. So that means that sulfur has 16 electrons. But we now need to ask ourselves how many valence electrons? How many valence electrons in sulfur? And the way you can do this is by drawing your shell notation. So if you can imagine you've got sulfur here, right? And your first shell is going to take 1, 2 electrons, followed by 3, 4, 5, 6, 7, 8, 9, 10, followed by 11, 12, 13, 14, 15, 16. Right, so now we've covered 16 electrons in sulfur. Okay, I'm going to make that full screen. So we've got 16 electrons here, but how do we get the valence electrons? To get the valence electrons, you look at your outermost shell, right, which is going to be this shell here, and you count how many electrons you have. So if we count here, you've got 1, 2, 3, 4, 5, 6. So your answer to this is going to be 6 valence electrons. And your last step is you're basically going to draw your 6 valence electrons. You first write down the symbol of the element they've given you, and then you place your 6 electrons around sulfur. The way we do it is we start labeling one of the electrons using a dot. You could also use a cross. So we've got 1, 2, 3, 4, and now we go all the way around again. So 5, 6. So this is our Lewis structure for sulfur. Okay. So if you ask to do another element, you follow the exact same process, but obviously it's going to be a different number of valence electrons and a different symbol here. Okay, that brought us to talking about something called stability. So we understand that stability is basically when the outermost shell of the shell is not filled. So in other words, if you go and you draw your element for sulfur, let's just look at sulfur. We can see that in the structure, we're looking at this picture here, we can see that there's 6 valence electrons in shell number 3. But we know that shell number 3 can actually take a maximum of 8 electrons. So there's still technically space for 2 more electrons here. So this means that the outermost shell is not completely full. And because it's not completely full, it means that it is unstable. And we know that any element does not want to be unstable. Everything wants to reach a level of stability. And that brought us now to bonding. Bonding takes place between different atoms because they want to become stable. But it's almost like they don't have enough electrons to fill their shells. So what they kind of do is they go to other elements and they steal or they give away electrons. And by doing that, they fill their outermost shell, making them stable. Okay, so that brings us to a concept called valency. Valency is the number we use as our guide to tell us how this process is controlled. So we've done a few examples where we actually go and find the valency numbers of different elements. But again, we've learned a shortcut on how to get our valency numbers by looking at the periodic table. So by drawing these numbers using this method we've learned, we basically figured out that we don't need to actually go through that long method. We know our valency numbers based on the numbers we write on the top here. So for instance, oxygen is -2. You can see in the periodic table. And what that means, if oxygen has a valency number, so if oxygen's valency is -2, what this means is, so the minus is firstly telling us something. It's telling us that it wants to take 2 electrons. So it wants to take 2 electrons from another atom. in order for it to become stable. Okay, so once we were done with learning those basics, we were now ready to go into chemical bonding. This is a guideline we can see highlighted in yellow here, which is giving us the definition of a chemical bond. You must learn your definitions for whatever they have in the guidelines, because in your paper they can ask you to define things and they expect you to give them the guideline definition. So that's something that you have to do, learning these guideline definitions. As I said, we're going to go through a few papers and we're just going to look at the pattern of what they're asking you, so what you should be able to know for your paper. All right, so we've got a few more examples here of drawing Lewis structures. So if you think you still do not have it figured out, you can actually take these examples here. You've got these elements and you can go draw your Lewis structure, and the answers are here, so you can check it against that. Right, so we talked about a chemical bond, but now we're going to talk about what is actually going on inside the chemical bond between the two atoms as they approach each other. So in a nutshell, what we described was, if we look at the picture at the bottom, you've got your positive charges and your negative charges floating all around in the atom. Now, if you put two atoms close together, we know from electrostatics that, firstly, if they are like charges, they're going to repel each other, and if they're unlike charges, then they're going to attract each other. So we know that the electron in this one atom wants to firstly attract the protons in this other atom's nucleus. So from there, we're going to get an attractive force. But we're also going to get two repulsive forces, firstly between the protons in the nucleus and then in the electrons floating outside. So you need to be aware of these three forces, but most importantly is the attractive forces. If your attractive forces are very, very strong, what's going to happen is these atoms are going to start moving closer together, and eventually that is going to form a chemical bond. So they come close together, they form this bond, right? And then we have a bond strength. Take note of the wording. When we talk about bonds, we talk about two atoms coming together, a chemical bond, right, between two atoms. And then bond energy, we defined it as how much of energy is it really going to take us to break this bond, right? So you can pretend you're taking a hammer and these two atoms are actually glued together, which is the bond, and you trying to pull them apart. So the proper definition from your guideline is the amount of energy to break 1 mole of a specific covalent bond in its gaseous phase. So the whole thing about bonds coming together is represented in this graph, which is a popular thing to be examinable as well. And the most important thing for you to understand here is what exactly is going on in this graph. So you've got, let's just write it on the side. You've got a graph that looks like this.